Okay, I asked you guys to go learn about the difference between dimensions and units. Hopefully you got it now. What is the difference? Well, a dimension is roughly, and sometimes I'll be on paper. We're going to try this. I'm learning how to use this surface a little bit. And I've got it facing me so the camera's on me, so it's a little awkward to write. Something we measure. That is a dimension. What are some examples of dimensions? Well, that's things like length, mass, time, temperature. A unit, then, what is a unit? Well, hopefully you found that a unit is basically a standardized quantity we use for measurement, for measuring a dimension. Units are going to be one of our biggest challenges in this course. Um, I always tell students if you, in a thermodynamics course, if your units work out, there's a good chance, in a thermodynamics course, maybe 60% of the time, the problem's probably correct if your units work out. If it's a fluid mechanics class, probably like 90% of the time, if our units work out, the answer is probably correct. Um, but yeah, so a unit is a standardized quantity or standard quantity we use for measurements. Used. You don't need the D on used, do you? Um, but let's talk about some of the common units we use here. Now, I'm teaching engineers to function in the United States. So we still use what often we refer to as the English system. I notice a lot of texts today often refer to it as the U.S. customary system or often just the imperial system because the English really don't like that moniker, I guess. I don't know. But they don't use it, right? So why would they call it? Why not be called the English system? I get that. Let's talk about what are some common dimensions that we would use. And I'm going to switch here. I'm going to stop share and I'm going to switch to the my document camera here. And I'm just going to write this out on paper. So dimension. If my dimension is length, for example, my dimension is length, for example, you can see it's a little better on paper. I don't know if it's a lot better on paper. This is going to be L1. This is going to be page one of something. Kind of keep me organized there a bit. In the System International, what we often just call the metric system, the SI unit for length, we're often going to use the meter. In the English or the what I will often just refer to as the English system because I'm an old millennial and that's what it was when I was taught. Again, the American customary or the imperial system, we will often use feet, which by the way, when I write units out, it will often be very quickly written, it'll be sloppy, and it will be written often in cursive because I was taught how to write cursive and I can write much faster in cursive than I can in print. You might occasionally encounter inches. Um, my puppy is asking to go outside. She can wait for just a little bit here. In the SIs, I'm sorry, in the English system, we might occasionally use inches. If you're not familiar with that, that's 12 inches in a foot. It's an arbitrary number, as is most things in the imperial or English system. We will have to learn to use both. I recognize that you may not have had much exposure to the English system in a science class or math class. But here, again, we're teaching engineers. Engineers do have to be able to function with either unit set. So we will encounter English or imperial-based units from time to time. Another dimension is time, the dimension of time. In both systems, we will use seconds. Occasionally, we'll deal with things smaller than a second, and so we'll use the SI prefixes of milli and micro from time to time, but the base unit is seconds. You'll also encounter hours and minutes and days. that's common in both the SI and the English system. If we do things larger than a second, we might use minutes and hours, and those are common conversions. Might occasionally use days. Okay? Another one is mass. Units of mass we'll encounter. In the SI system, we'll often use the kilogram. Again, I very rarely write that in block or print text. I'll often write that in cursive. So my kilogram is going to kind of look something like that. In the English system, there are two units we can use. LB with the subscript M is pound mass. And that's often how it will be written. I'll try to make my M's a little more clear, but that's often how it will be written when I'm writing it in a hurry. I will always write my units, almost always write my units. They might not be pretty. They might get kind of scribbled down and you'll get kind of used to what that looks like. If you need to write them more clearly in your notes, you know exactly what they are. You'll get kind of used to what a kilogram looks like when you write it quickly. And if you can just aggressively be very consistent about it, this is often how I will write pound mass. Now you might also encounter the slug in the English system. In this text, as with most thermal science texts, we rarely use the slug. Slug is pretty common if we're dealing with structural or more mechanical type courses. And we'll talk about there is an advantage to using slugs. There's also a disadvantage to using slugs. We'll talk a little more about that once we get done talking about force. Right? We talk about force in the SI system. The base unit is the Newton, right? And this is the kilogram, by the way, in mass. With the kilogram, of course, is 1,000 grams because a gram is a very small quantity. We often use the kilogram as our base, but it's not inappropriate to use grams. We just won't do it very often. But we do typically start with the base unit of Newton, or often work with kilonewtons also, or meganewtons, depending on how large a quantity we're talking about. But at any rate, we will use kilograms more than we'll use grams, but we'll use newtons, kilonewtons, etc. throughout. In the English or imperial system, there is a unit called the pound force, LB with a subscript F. And again, if I'm writing that in cursive, it's going to look something like that. The pound force. If there's no subscript on a pound, on an LB, you should just assume that it is pound force. In this text, because we use both pound mass and pound force, you will want to subscript those two because they are not the same. One measures mass, the other measures force. Now, how do we, what do we do with that? Well, I'm looking at my PowerPoint slides here. Okay. I apologize. Well, remember from physics, force is equal to mass times acceleration, which of course is length per time squared. Right? Mass times acceleration is force. So any unit of force can be broken down into a unit of mass times a unit of length divided by a unit of time squared, meaning your conversion factors will always work that way. We know kind of the SI system. We don't even think about it a lot of times. You just kind of get used to the SI. Well, it's the SI system. The units cancel out, right? 1 Newton is the same as 1 kilogram, or 1 Newton is the amount of force required to accelerate 1 kilogram at a rate of 1 meter per second every second, or 1 meter per second squared. So if I'm to write this as a conversion factor is a quantity that's equal to 1. So if I solve this for 1, well, that means I'm going to move basically everything on this side of the equation over here. So 1 is equal to 1 Newton divided by 1 kilogram meter per second squared, which complex fraction says the denominator of the denominator can go then to the numerator. So that means that 1 Newton second squared is the same as 1 kilogram meter. And this becomes a conversion factor. And again, we don't think much about applying this, but this is technically how you would go from having kilograms to newtons. I would apply this conversion factor. So for every newton second squared, there is 1 kilogram meter. Now, in the English system, 1 pound force is the amount of force required to accelerate one slug at a rate of 1 foot per second, or 1 foot per second squared. The slug is the English unit of mass that is 1 to 1 in terms of pound force to slugs, meaning that conversion factor, something that equals 1 here, for every pound force second squared, there is 1 slug foot. Okay, that's fair. And it's the same. You can see it's the same logic to go from a collection of slugs, feet, and seconds. You would use the same logic we would use for the SI system to go to pound force. Now, what we're going to do in this class is we're going to use the pound mass. So 1 pound force is the amount of force required to accelerate a mass of 1 pound mass at Earth's standard gravity of about 32.2. I think it's 32.174, but 32.2, three significant figures is going to be just fine for us. That's Earth's standard gravity in units of feet per second, or feet per second squared. So what that means is if I have a collection of pound mass, feet, and seconds, and I want to get rid of the pound mass and go to pound force, that means for every pound force second squared, there are 32.2 pound mass feet. What does that mean? Let's say my mass is equal, so an example here, let's say I've got a mass here of 5 pound mass, and I want to find the weight. Well, how do we find the weight? Well, the weight, of course, is equal to mass times gravity here on Earth, or the gravitational acceleration locally. On Earth, it's going to be 32.2. So this is going to be 5 pound mass. I'm going to multiply that by 32.2 feet per second squared. And this is going to work out to be, I don't know, what is this? It's going to be a 5 plus a 1, so it's going to be 1/6. And this is going to be, I'm going to add a 161 pound mass feet per second squared. Now, the rookie mistake is to just assume this is pound force. This is not pound force, because for every pound force second squares, there's 32.2 pound mass feet. So I'm going to have to apply this conversion factor here that if I want pound force and not pound mass, I need to apply that there are 1 pound force second squared for every 32.2 pound mass feet, which means my weight is going to just come out to be 5 pound force. So about to the end of this video here. What is the advantage here? Well, if I use slugs, I don't have to worry about this factor of 32.2, but then I have to know what is a slug, right? And I don't know, I mean, I know I weigh about 190, 195 pounds. That's my weight, that's my pound force, which means I have about 195 pound mass of mass. I don't know how many slugs I got. I'm sure I could learn that, but I just don't think in that way. If you've grown up here in the States, you tend to think in pounds. You probably have learned how to think in pounds. I know other parts of the world, they think in terms of stones. A lot of parts of the world, they think in terms of kilograms. And these are all fine. It's just different ways of measuring your weight, how much force the Earth applies to you towards the center of the Earth based on the gravitational attraction between you and the Earth. Anyway, it's just conversion factors. So you want to, I'm about to run out of time here, but I'm going to put big green stars around this because I can't find my red pen quickly. If you're in my class, you get one sheet of notes when you take an exam. Handy thing to have available. Handy thing to have available whenever you're working these problems out is this quantity right here. For every pound force second squared, there are 32.2 pound mass feet. It's real easy to see why that's important when we're finding weight, but it might not be as obvious when I'm trying to find the kinetic energy, right? If I'm trying to find the kinetic energy where I've got mv squared, so I've got pound mass feet squared per second squared, well, you do have to understand that I'm going to have to apply this to get rid of the pound mass and go to pound force. And then with pound force feet, I can convert that to BTUs or joules or something else useful. All right, that's a good discussion of units. You can probably hear my dog Hazel asking to go outside. I need to take her outside. So I'm going to stop there and we'll pick up there next time.